All right. Okay. So we are in the next lesson for Unit 4, which is starting to build up to this idea of this word integrals that I keep talking about. Now, in order to get there, we're having to learn some stuff first. Like yesterday, we learned how to do sigma notation. Today, we're learning about approximating. Okay. Again, you're probably noticing this is following a very similar path to how we did derivatives. With derivatives, we learn limits, and then we learn how to approximate average rate of change. What we're doing now is we've learned sigma, and now we're learning how to find areas and distances, okay, which is what an integral ultimately does. It finds exact area and exact distance traveled, predominantly area for what we're talking about today. More specifically, an integral finds and calculates the area underneath a curve bounded by the x-axis, which we're going to talk about in a lot more great detail when we actually get to the definition of an integral. But I want you to think about it. Like in this example here, we're looking at the equation y equals negative x squared plus 4. I got it written down twice. And what I'm wanting us to do is find the area on the interval 0 to 2. I want us to find the area underneath the curve 0 to 2 bounded by the x-axis, which that piece of the graph is already given to you right here. That's the piece of the graph, negative x squared plus 4, which means 0 to 2. And I'm wanting to look between 0 and 2 bounded by the x-axis. And I'm wanting to find this area here. Well, finding area underneath the curve is kind of difficult when it's a curve because we can't just do base times height or length times width or anything like that because of the curvature. Like, how do we figure that out? Well, integration is going to be the answer to that. But for now, all we can do, just like when we were doing average rate of change, all we can do is just approximate the area underneath the curve. And just like how we created a definition from the approximation of average rate of change, we're going to do the same thing with approximating area. So today's lesson is all about finding, an approximation for the area underneath the curve. There isn't a strategy for doing that. Okay, it's actually a guy that came up with it called Riemann. So we call this approximation Riemann's sum. Riemann's sum. So that's the lesson for today. It's learning how to approximate area underneath the curve using Riemann's sum. So you can write approximation of area under a curve. And that area is going to be bounded by the x-axis. Okay? So I kind of outlined it right here on the left. Now we're going to start off with talking about two different types of Riemann sums that we use to approximate area underneath the curve. And the first one is called a right Riemann sum, and the second one is called a left Riemann sum. Okay? So let's start off with the right one. A right Riemann sum approximation for area underneath the curve. How we do this is we try to outline the area underneath the curve with shapes that we know how to take the area of. And more specifically with Riemann, he uses rectangles. So let's write this out. This is rectangles made from the right, in this case for right Riemann sum, it's made using the right y value on the subinterval. And we'll explain how this looks in a second. Okay. Now, what I mean when I say subinterval, okay, what I mean when I say subinterval is we're going to use a specific amount of rectangles in order to approximate the area underneath the curve. And that's going to be specific to each problem. So for instance, in this problem, I say, all right, This is my curve. I'm approximating the area between these 2 points, and I want us to approximate it using, in this case, let's use 4 rectangles. Okay, 4 rectangles. So, the interval here would be to take your domain, and I want you to divide it by the number of rectangles we're using to approximate, which in this case, my domain is just 0 to 2. So we're going to say, and we're going to call that b minus a over n. So if I'm going from a to b, the length of my domain would just be the difference between the two. So in this case, my domain is 2 divided by n. Okay? So we'll do this example up here in a second. Now, whenever I'm finding the area of each of these rectangles, whenever I'm finding the areas of a rectangle, I want you to remember how area of a rectangle works. It's just base times height. Okay? Now, the base, the base is going to be this b minus a over n. It's going to tell me the length of each of my rectangles. So, what I want us to do is I want us to substitute in b for b minus a over n. And the height is going to be the y values of the right side of my rectangles, which I'll call f of, we'll say x sub I to represent the multiple different x values that we use. Okay? So let's go up here on our picture and show exactly what this looks like. All right. I am wanting us to use 4 rectangles. And that changes per problem, but this problem it's 4. So if I'm going from 0 to 2, if I want to know the intervals or the lengths of those rectangles, you simply do 2, I'll do it right here, 2 minus 0, or b minus a over n, or 4. And in this case, that's equal to 1/2. Hopefully that makes sense. That means that every length of 1/2, and if you're looking on this, this graph here, these are lengths of 1/2. So if I divide this into 4 equal lengths, these are 4 rectangles with lengths 1/2. Do we see that? Okay, that's what I mean when I'm talking about the base. You just take your interval and divide by the number of rectangles, and that tells you the length of your rectangles. Now, if this is going to be a rectangle right here, this is my first rectangle right here, okay, right here. Then a right Riemann sum uses the right side of the rectangle to approximate. So that right side is going to touch the y value up there. So that is my first rectangle. My second rectangle is these 2 sides, and it's the right side of this rectangle that's going to be touching my graph. So you see, Riemann sum uses inscribed rectangles. The right side is a right Riemann sum. So if I'm using the right side of my rectangles, and the right side of this rectangle is just 0, so there is no rectangle there. Okay. So what we do is we figure out the areas of these 4 rectangles and add them up, and then we have an approximation for the area underneath the curve. Now the question I always like to ask is this going to be an under approximation or an over approximation? Well, I think it's pretty clear to see that it's going to be an under approximation, because look at all these gaps of the areas that we're missing by doing a right Riemann sum. Okay. So that's probably worth noting. If we have a decreasing function, a right Riemann sum is going to be an under approximation. But let's figure out this area's approximation by doing this. Let's see what we got. Okay. So, the area equals. Now, what I'm going to do is take the area of each of those rectangles, just base times height. So the base, so let's do the rectangle for the first one. The base is 1/2, and the height is going to be whatever that y value is. Whatever that y value is. So the y value is this y value here. or just whatever f of 1/2 is. That's that height right there. So I'm going to say, I'm going to do it like this. Say 1/2 times f of 1/2. That's base times height. The second rectangle is going to be base is 1/2. And then the height, if we look at the top here, is the y value right here, right? Isn't that the height, which is just f of 1, the y value there. So f of 1. And then the third rectangle is going to be 1/2 times f of, the next interval would be 1.5, or f of 3/2. That's the y value there. And then lastly, that fourth rectangle, which isn't even a rectangle at all because it has no dimensions, is 1/2 of f of 2, okay, which is the y value right here, okay? So we're going to figure out those four areas and add it up and see what we got. Okay. So area equals, all right, just figuring out those values, and I just did this in my calculator because remember that f of x is equal to negative x squared plus 4. So I just plugged all of these values into that function to figure out those heights. So what I got now is 1/2. And let me go ahead and tell you kind of like how I like to write this from here out, is because they all have an equivalent base of 1/2, I just take that out as a GCF, and I'm left with f of 1/2, f of 1, f of 3/2, and f of 2. So what I'm left with is, I'll just go ahead and show that, f of 0.5 or 1/2 plus f of 1 plus f of 3/2 plus f of 2. Which when I computed those values, f of 0.5 was 3.75, f of 1 was 3, f of 3/2 was 1.75, and f of 2 was 0, so we didn't even have a rectangle there. And the final answer I got was 4.25 units squared. So the area underneath that curve is approximately 4.25 units squared. And we know from looking at the picture above that the real area should be bigger than that. The real area should be bigger than that. So now let's see what happens whenever I do a left Riemann sum. So I'm sure you can imagine what that means based off of how we did the right Riemann sum. So let's write that out. A left Riemann sum, I think I keep spelling this name wrong. If I do, I'm sorry. A left Riemann sum is the exact definition of a right Riemann sum, but we're using the left y value now to create our rectangles. So these are rectangles made from the left y value. On the subinterval. Okay, so let's draw that out and show what that looks like. Okay, so again, we're looking between 0 and 2. So the area we're finding is this shape right here. The area underneath that curve bounded by the x-axis. So our subintervals is we're still using 4 rectangles. That's specific just to this problem. I say, so that's still 2 divided by 4 is 1/2. So it looks like this. These are the bases of my 4 rectangles. But now, like for instance, if I'm looking at this first rectangle, the left side of it is what I'm going to put as the y value. So right there. Now, if I draw the right side all the way up, notice how it goes above the function. Okay. Now, same thing here. If I'm using this as my base for my second rectangle, we're going to extend the left side and touch the function and draw my rectangle from that. Same thing for this one. All right, if I'm drawing a rectangle, it's going to go up to the left y value and make a rectangle. And same thing for this last one. The left side is going to touch the function and make a rectangle. Okay. And now we're going to take the area of these four rectangles. So I'm sure you kind of see where I'm going with this, but do you think that's going to be an over approximation or an under approximation? And I think we can clearly see that the rectangles formed go past the curve. So you can see that this is going to be an over approximation because we have more area accounted for than what's underneath the curve. So with a decreasing function, a left Riemann sum will always be an over approximation. Okay? So let's figure out the area of the rectangles made by those four. So I'm going to say, and I should have wrote this on the last one, but we'll denote the left Riemann sum as L4, meaning a left Riemann sum with four rectangles or four subintervals. And I'm going to set it up just like the last one. I mean, it's still going to be 1/2, okay? 1/2 for all the bases, and I'll go ahead and take that out as a GCF. But on top here, it's now starting off with f of 0, and then f of 1, and then f of 1/2, f of 1, and f of 3/2. So it's using those four numbers as the heights. So I'll write that out. It's f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. Okay, those are the four heights we use. So, and most of those we've already found in the previous problem. F of 0 is 4. We already know f of 0.5 is 3.75. That's 3, and that's 1.75. So, if I approximate the area using those values on the left side, I'm getting 6.25 units squared. So, the left and right, all they are approximations. One will be an over approximation, one will be an under approximation. It doesn't give me an exact answer, but shoot, it does give me a pretty close approximation. I got 4.25 units squared as the lower and 6.25 as the upper. I know that the actual area is somewhere between those. I know it's going to be greater than 4.25 and less than 6.25. So all we have is an approximation, all we have is a bounds. We're going to learn later on down the road with integrals how to find the exact area underneath the curve. Okay. All right. So that was left Riemann sum. That was right Riemann sum. And you're probably even thinking maybe, well, what if we did something a little bit better? What if we did midpoint Riemann sum? What if we kind of average the two out a little bit? So I'm going to end with this problem. And we're going to pick back up with some more in class. But I'm going to end with teaching you midpoint Riemann sum. But it's the same exact thing. So we're going to do the same problem. We're going to do y equals negative x squared plus 4. I'm going to say that we're finding the area between 0 and 2. And lastly, I'm going to say that we're going to use 4 rectangles. Okay, 4 rectangles here. Now, a midpoint Riemann sum, I'm going to give you a quick definition of that. It's the same as the other two. It's rectangles formed though, but the y value is the midpoint of each subinterval. So rectangles formed by the y value of the midpoint of each subinterval. Okay? So, if that's the case, I'm looking between, again, this value and this value, so that's my domain. I'm bounded by the top of this curve and the x-axis. This is the shape we're making. We already have an under approximation. We already have an over approximation. I'm curious to see what's going to happen with midpoint. Okay? So we're still doing 4 rectangles. So the subinterval is still the same. It's rectangles with length of 1. We already know that because we did b minus a divided by our n value to figure out those lengths of our rectangles. That's 1/2. So we're still creating rectangles, but for this first rectangle, it's not the left y value, it's not the right y value, it is the value right there in the middle of the two. So not 0 or x equals 1/2, but half of that would be x equals 1/4. That's the y value we go to. Now, instead of doing this side of the rectangle or this side of the rectangle at at x equals 0.5 or x equals 1, we're going to do it right in the middle of that, which is 1.25. Right here is the midpoint of the two rectangles. And right here is the midpoint of the two rectangles. And right here is the midpoint of the two rectangles. So, it's not going to be an exact, but it's going to be quite better than the other two, because you notice how, like, if I find the area underneath these rectangles, notice how, like, both of them go both out and inside the curve. So, like you have this piece on the outside, this piece on the inside, this piece on the outside, this piece on the inside, this piece on the inside, this piece on the outside, this piece on the inside, this piece on the outside. So it's almost like you have like part of the end of the function and the out of the function. You have those kind of like canceling each other out. So it's going to be a pretty dang close approximation. It's not going to be exact, but it's going to be a better approximation. And really, there's a way to tell if it's an over or under approximation with midpoint. It's not like the fact that it's decreasing doesn't really tell us that. It's the fact that it's decreasing and concave down, that midpoint. So I'll write that out real quick. Concave down and decreasing means that a midpoint approximation is an over approximation. The fact that the function is kind of bowed outward, think of that for concave down, it's like bowed outward, and it's decreasing means that it's going to be an over approximation. Okay. But anyway, let's do the math real fast. And the process is the same. It's the midpoint Riemann sum using 4 subintervals. The base is still 1/2, so I can still pull that out as a GCF. It's just the heights are a little different. So we got these 4 heights, which are halfway between these x values, which I kind of already discussed. Halfway between 0 and 1/2 is 1/4, right? And halfway between 1/2 and 1 is 3/4. And halfway between 1 and 1/2 is 1.25, which is 5/4. And halfway between 1.5 and 2, isn't that 1.75 or 7/4? But I'll let you figure out what these y values are and add them together if you want. But the answer ends up being, so the midpoint approximates us 5.375 units squared. So notice how, like, if you compare that to our last answer, the under approximation was 4.25, the over approximation was 6.25, and notice how the midpoint fell in between the two. So it's a little bit better of approximation. Okay. So that's all we learned today, is approximating area underneath the curve, bounded by the x-axis, using a certain amount of rectangles. Now, a question I want to leave you with is, how could I have a better approximation of the area underneath the curve? Not talking about the difference between midpoint and left and right, but what is something we could change in this problem? Can't change this. I can't change this. But what else could I possibly change if I want to approximate a better area underneath the curve? What if I change this number? How would changing that number better approximate the area underneath the curve? So think about that. And honestly, that can help you with this next problem here. If you want to try this on your own, we will do it together in class, but it is another example. This is actually the example x squared. I want us to look, if we're looking at the graph here and how it's bounded, I want us to look at this one. Again, between 0 and 2. We'll look at it between 0 and 2. It's the same graph, so 0 to 2. The area bounded from this curve, try to approximate this somehow. And I'll say, instead of 4 rectangles, let's approximate this using 8 rectangles. Let's see what that looks like. Okay. All right. Try this one on your own. We'll do this in class tomorrow, and then we'll finish up with a few chart examples, which is how they love to ask this question on the final exam. All right. All right. Good job today, guys. We'll pick back up later.